Hello, this is Patrick O'Shaughnessy, and this is the 18th module in the series Statistical Methods for Analyzing Data Obtained in the Lab or Field. In this module and the subsequent three modules, we'll be exploring some of the statistical concepts associated with conducting experiments in a lab and or field that are important to understand while you're conducting them, such as, what is an LOD? What kind of error are you propagating? How do you compare instruments? Those kinds of concepts. So it is assumed that you have already viewed the modules 1 through 12. The first set are those associated with linear regression analysis and even test on the slope and the intercept, which will be discussed in these modules, as well as the concepts of a two-sample t-test and a pair t-test. So let's get started. The first kind of simple concepts are associated with the types of measurements you're making and how they result relative to the expectation, right? And that expectation is what we call the accuracy. So here's the kind of the classic scenario of someone shooting their arrows at a bullseye target. And we see that, for example, in the upper right, we have the ideal scenario where our 4 arrows have landed on the bullseye and they're clustered very closely within it. So we have both high accuracy, we hit the bullseye, and we have high precision. They're closely clustered around the bullseye. We could also have high accuracy but low precision. We're scattered around the bullseye or trying to hit it, but again the scatter is now higher, so the precision's low. And or opposite kind of scenario where we're really good at putting it where we cluster it, but not where we want it. So we have high precision, but low accuracy. We're off always by some amount. And then finally, the worst case scenario is the bottom left, where we have both low precision and low accuracy. So getting back to this concept here in terms of our measurements, let's take a look at the issue of low accuracy, high precision. So we have, for example, not just 4 samples, but maybe 20, enough to create a distribution of those samples. So we can look at it from this perspective that we have, again, this distribution around some mean value here. But that mean value is off from where it should be, right? The reference value, in this case, the center of our target. So we can think of that distance between the reference value and the average as our accuracy. How far off are we? And the relative difference here, the spread of our distribution as the precision. It's not exactly that way depending on the definition, as we'll see, but this is a good way of visualizing what's going on from the standpoint of your data points. Here is a definition of precision. There's one of several. There's different types of definitions for precision, but this is the most commonly used, where it's the relative variability of measurements about the mean of the measurements. So to calculate it, simply the standard deviation divided by the mean. You may also see that same calculation expressed as the coefficient of variation, or CV. And yes, they are identical in that regard. So here's an example of manipulated by me in a spreadsheet so that the precision is always 15%. But you can see here, just to emphasize the point, that 15% for a standard concentration of 10, as shown here, has much larger error about it than would be the precision of 15% about a standard concentration of 1. So you have to keep that in mind when dealing with precision as defined this way. Here's another definition for precision you may find out there. It can be calculated as the average positive or absolute value of the difference from the mean. So you can see here it's the summation of the absolute value of your measurements, y sub I minus their mean, and then you're taking the average of that difference. So this is actually not too far removed from the definition of standard deviation itself, which gets around the problem of summing up yi minus y bar will ultimately get you to 0. So you either have to have the absolute value or you square that summation to have something other than 0. And because of the inherent bias of that estimate relative to the true standard deviation sigma, as we know, you have to divide through by n minus 1, take the square root of the whole thing. So this is this definition of precision is not relative to the mean. It is an indication of this overall spread of the values. And here's the definition of accuracy. Accuracy is the ability of a method to determine the true measurement, we'll call it T, from the environment sampled. So it is your ability to be able to do that. How well can you, how accurate are you, so to speak, right? How accurate is your measurement? That doesn't really allow us to get at a calculation for it. So interestingly, we use the concept of bias, which is in a sense the opposite of accuracy. If you are not accurate, then you are biased. And so that's the relative discrepancy between the mean of the measurements y bar and this true measurement t, if you know it, which can be positive or negative. So now we're able to come up with a calculation here of bias, which you can see is again the relative discrepancy, meaning y bar, the means of your measurements, minus this true measurement divided by the true measurement. So you can also express it as y bar, the mean, divided by the true measurement minus 1. So back to our diagram then, you can see that you could look at this either way. The diagram shows the word accuracy in it, but that shift away from the reference value is truly the bias. So you can see how they're inverted to each other, but the same concept. So bias is calculated, accuracy is not. So let's have an example here. So let's say we are using a balance to weigh a standard weight. So we know exactly what it's supposed to weigh, of 25 milligrams, and we weigh it 10 times. So what's the precision and bias of your balance? Well, you weigh it 10 times, you record each weight, take the average of those, you end up with 24.753 milligrams. So this is what's called a 6th place balance. You're down to all the way down to a thousandth of a milligram, which is a microgram. So we have a standard deviation of 0.019 milligrams. So we just go through these simple calculations. The precision is the standard deviation divided by the mean. We end up with 0.0008, which is 0.08%. So we're plus somewhere near 0.1% for precision. And likewise, the bias is the mean, 24.753, divided by the known weight, the t, capital T, 25, minus 1, which gets us to around minus 0.01, which is a negative 1% bias in this balance. Now, sometimes you'll read about error. And how does error relate to precision and accuracy? Well, one term is systematic error, and that truly is just another term for bias, as you can imagine. So it's systematic. You can't. It's always there. It's always forcing you off the truth. So it's a shift in all measurements in a systematic way, so that the mean value is constantly displaced or varies in a predictable way. Once you know what that bias is, it's predictable. Okay, then there's also this concept of random error, just the way it sounds. It's another term for precision, right? As we discussed, standard deviation is a kind of an estimation of randomness, right, about a mean. So this is the error in measurements that actually is kind of unpredictable. It is because of its randomness, you never know whether you're going to be a little bit negative or a little bit positive from your average over time. Sometimes they call this the instrument noise, right? Or how sensitive is the instrument. relative to background fluctuations, for example, or whatever else is going on with your instrument. So these two terms put together can ultimately derive a total error between kind of your bias and your precision, otherwise known as systematic error plus the random error. Gives you a total error in your measurements. So as an example, here's something out of my lab where we use a pressure sensor to measure the change in air pressure caused by breathing through a respirator. Yes, it takes a little bit of a pull on your lungs to force air through the media of the filter. So you can put a sensor as shown here in a way that's measuring the air pressure inside the mask relative to another probe that's measuring atmospheric pressure as you're breathing through it. And you have it hooked up to a system that gives us a reading every quarter of a second. And this is a output for 100 of those measurements, which is a total of 25 seconds worth. So each little squiggle is a measurement. So you can see it has noise in it as we would describe it, right? There's a variability here, and it can be easily assessed as a mean of 20.19 millimeters of water pressure and a standard deviation of 0.14. So with those measurements, now we can get at the random error, which again is simply the precision, which is the standard deviation divided by the mean, which is 0.14 divided by the 20.19, which gets us to about 0.7% random error. So at any given time, this measurement is plus or minus 0.7% of the truth of the average of that measurement. Now this is getting at the random error, not the systematic error. The sensor was zeroed, as it's called, before making these measurements to ensure that when there is no pressure, it's giving a reading of 0 millimeters of water pressure. So the total error then is 0 plus 0.7%, which equals 0.7%. Now here's some information from an instrument manufacturer, which is always something worth checking out. Usually this kind of information is on the very back end of the manual, or sometimes it's part of a brief PDF given out to demonstrate the instrument's capabilities, but you should read these carefully. So here's something from an aerosol concentration meter that I have used, and you can see, hey, there's those terms, precision, accuracy, and then resolution. Well, the precision, as we know, is this, as expressed here in percentage, 2%. 0.2%. So it's interesting here to note that the precision varies with what they call the averaging time. So if you see the lower precision of plus or minus 2.2% here is related to a very quick averaging time of 1 second. So it's not as precise when it's trying to give you a value as quickly as possible. It gets more precise, 0.2%, when it is allowed to think longer, so to speak, or include more measurements, which makes sense, a 60-second averaging time. The accuracy is plus or minus 5% of the readings. I'll talk about this next part. So again, that's also expressed as a percentage. So this is the bias is plus or minus 5% at any given time, but we don't know whether it's plus minus 1% or 2%, but it's within that range. And the resolution I haven't talked about yet, but that is the lowest increment between one reading value and another. Especially with the digital world we're in, you have to have an increase, say, in aerosol concentration of a certain amount before the instrument goes, oh, now this is a higher level. I'm going to be responding with a new number that's higher than the old number. And in this case, it's saying it's at 0.1%, or this value of 0.001 milligrams per meter cubed. When it gets above that, it will change its output. So that's the resolution. Now back to this accuracy definition of plus or minus 5% of the reading, plus or minus the precision. So they're including the bias here, that they're calling the bias accuracy. And they're also tacking on the possibility of the precision here, adding to a greater level of being off, right, by the amount of the precision here on the positive side, the positive precision. Of course, it's also plus or minus the precision, so it demonstrates that this bias is also influenced by the variability of the random component or the random error of the instrument. Now here's another look at a document. In this case, it's an actual method established by a government agency. And you'll see here that it gives indications of the type of sampler that is to be used, the flow rate at the sampler, the technique associated with measuring. But down below, you'll notice that it has indications of bias, precision, and accuracy. So it says the bias is none, and then it says see reference 2. In reference 2, it says that this method is so good that it is considered the standard method, and therefore it is unbiased in that regard, not in the same sense that we have been talking about here. Whereas the accuracy at the bottom is the type of, in a sense, bias that we've been talking about. In this case, it's plus or minus 16.7% at this low level of 23 micrograms per meter cubed. So a little bit of confusion there, and so sometimes you have to dig into the references to determine exactly what they mean by bias, precision, and accuracy. They have an overall precision here based on a concentration of micrograms per meter cubed. They also have a precision over here, which is based on the mass of particulate matter, in this case, that is collected on a filter. And so you can see then it's in units of just micrograms versus a concentration. So again, you have to be able to dig into things a little bit, but the point is that methods also should report these indicators of precision and accuracy. You may have heard of the term a blank, and so we'll just talk a bit about 3 different types of blanks. First, I'll refer to as a lab blank, and I say I because I'm not sure if I found any specific universal definitions for different types of blanks, and so you'll have to be careful again in terms of how this term is used. But in my world, a lab blank is a media that is left in the lab, and for example can be used to determine if there's random fluctuations in an instrument. I'll explain that in an example. As versus a field blank, which is something you carry with you if you're going out into the field or even into another portion of the lab. It's basically the idea that you have some media that is handled in every way that your actual sample is handled, except it's not, as I'm saying here, submerged in the sample media, the air, water, soil. So you're allowing yourself the knowledge of whether or not just the way you handle it, how you put it into a sampling device, for example, etc., that may influence the result down the road. So if you are truly doing a field study, meaning something outside, you would bring it with you, and then it would be subjected to environmental conditions, right? The humidity of the atmosphere and that sort of thing, which may also somehow affect the media that you're taking your sample on. And then if you have it, you will then use it to determine whether the sampling process affects the sample media to the point that an adjustment is made. This is not always the case, but for those situations in which this does occur, you would then have your sample measurement would be subtracted from the field blank measurement, which should be really low. It should be down near 0, right? You haven't really collected anything, but it may be negative or it may be positive, in which case your adjusted measurement will be somewhat lower or somewhat higher than the sample measurement. This is true for indoor air exposures to workers, for example, under OSHA requirements. However, the EPA, for example, doing atmospheric particulate matter measurements do not apply a field blank measurement. They don't assume that everything that happens to anything that happens to the field blank happens to every other sample as well. So this is kind of a philosophical issue, and you have to, again, dig into whether or not this is a standard practice to adjust by way of the field blank or not. Okay, a third type of blank is what I might refer to as a method blank, or again, simply, in this case, the blank. And this is for any type of analysis, again, for which you are collecting your material, whatever it happens to be, onto a media of some sort, which then goes to a lab for analysis. And you need to have a blank that goes along with your samples in order to determine whether or not there's any substance on the sample media, some sort of contamination that would cause the measurements to be biased, again, right? Simply because your media itself has been contaminated by the same thing you're trying to sample. So in all cases that you would, for example, make a collection of different sample types that has to be analyzed by a lab, you would always send at least one blank, if not two, for them to determine, for you to say to the world, yes, this media is not contaminated in any way. And with that, we'll end this module and continue on with module 19.